This presentation, it's the continuation of the previous one in last session, and we will review several aspects of geographical information systems as applied to hydrologic and hydraulic modeling, and particularly related to hydrobead flood. The contents of the presentation are divided in three parts. We'll first review the coordinate reference systems and some basic concepts of these systems as geoid, ellipsoids, and datum. Then we'll take a look at aerophotogrammetric surveys and some other type of surveys as LiDAR. And then we'll finalize with techniques for making modifications to the digital elevation models, which is a very important part that we often need to do when we get a terrain to work in hydrobead flood. So first, the coordinate reference systems, or sometimes called CRS. So the main issue is that when we're dealing with surfaces on the Earth, what we encounter is that the Earth is not a perfect sphere. It has an irregular shape that is not easy to represent. If it was a perfect sphere, it would have been easier to make projections and all kind of things, but since it's irregular, then to have a precise representation of the surface is something that is really demanding. We're going to be looking at ways to represent the Earth's surface in a way that is practical for model use in particular. And for that, we are going to look at some concepts that are key in that type of representation as geoid, ellipsoid, datum, and projection. A coordinate system or coordinate reference system defines the spatial location of the data and also the relationship between the different elements on the surface. In a geographic coordinate system, like the one we would need to have in the Earth, it needs to be a spherical coordinate because it's similar to a sphere, even though it's not perfect, but it's the best coordinate system that we can have to represent the form of the Earth. And for that, we use a vertical angle, the horizontal angle, and the distance from the center. So these are these spherical coordinates that we use standardly to represent a point on the Earth's surface. And for that, as we all know, we use parallels that are lines that we can consider horizontal with respect to the axis of the sphere, and meridians that are depicted here. So these are the latitude represented by the parallels and the longitude represented by meridians, with an origin that is for the meridians in the Greenwich meridian, and then for the equator, for the parallel that is the biggest parallel on the Earth. Now the geoid is a geometrical form that we use to represent the Earth's surface that is not, as we said before, a perfect sphere, and is determined by the equipotential surface of the Earth's gravity field. So it's an idealized surface. It's not the exact real surface of the Earth, but it's an equipotential surface based on the fact that there is a force trying to pull to the center all the objects on the surface. And on the other hand, we have a mathematical definition of the geographic coordinate system that is done by representing the Earth, that is the geoid, by means of an ellipsoid. So in this sense, the ellipsoid is another form, but it's a mathematical form. It's not related to the physics of or the actual form of the Earth, but it's an approximation that we can manipulate in a much easier way. So these two geometries, if we want to call it this way, we're going to be dealing with, or we need to deal with those in order to understand how to represent a coordinate system in the Earth that would make sense to model hydrology. The graph that you see on the screen represents the differences in elevation between the ellipsoid and the geoid. So these two surfaces are not equal, and depending on the difference in gravity, but since the ellipsoid is a more idealized form, there are differences in different parts. So you see some areas here where the difference are, in this case, the geoid is about between 50 and 70 meters above the ellipsoid, and some areas where we have the opposite, where the geoid is lower than the ellipsoid that represents mathematically that surface. And we do that in this WGS 84 that is kind of a standard to represent the elevations on the Earth surface. So the ellipsoid or reference ellipsoid is used to describe the shape of the Earth using an ellipse of revolution. If you make a cut on that ellipsoid that represents the Earth, you would see an ellipse like this with a major and minor axis defined by A and B. And this, obviously, they are different because they represent since the Earth is kind of flattened sphere, the minor axis is smaller than the major axis. So in addition to these concepts, we're going to be coming back to them during the analysis of a DEM. We also need to use the datum. The datum is extremely important because there are many different standards or datums used in different areas, and even in a given area, there are some data that may be available in different datums. And it is important to know, if you are getting some data from a third party, what datum are they using, because they will reflect the elevation of the surface that you will be working on. So the datum is a reference point that anchors or link the ellipsoid used to the Earth's geoid. So it's a kind of the zero from which you measure the elevation in the Earth for a given projection. So if you look at the graphs on the left, you would see two approaches to the datum. The classic datum is kind of more adapted to the different areas on the Earth because it changes from area to area, so it's not an absolute datum for everywhere. And then you have the modern geodesic datum, like the WGS 84, that it's common to all the points on the Earth. And this is the one used by the GPS data that you normally collect with the GPS instruments. So the thing that's important to remember here is that when we are setting datums, we use different ellipsoids and also the same ellipsoid but in different positions. It depends on the standard that we are using to define the datum. Also, we need to remember that the GPS, so any GPS that you get that obtains its position from satellites, measure the heights with respect to the WGS 84 ellipsoid. So this WGS ellipsoid is the standard modern common datum for the whole Earth's surface. And the point here is that you need to understand that this is different in general from the datum that you would get from a geoid, that is a different surface. So it's a kind of confusing, but I think the graph here explains it very, in a better way. So this is a cut on the surface of the Earth, and you have here the ellipsoid that is a mathematical representation of the Earth's surface. Then you have the real surface, and then you have the geoid that is the generated by equipotential lines based on gravity. So you see here that there are differences, and that is not a problem provided that you can know for a given DEM what are the difference between the ellipsoid, that is the one used for GPS, the geoid, and the real surface. So all of these concepts, we're going to be coming back to them, but it is important that you keep in mind that they are very important to understand both the characteristics of a given digital elevation model and also to know for if you want to use a digital elevation model, it's important to know what are the characteristics of the specific product that you're using. And then the third thing to remember is that the graphical coordinate system is not unique. It depends on the ellipsoid and is set to respect to the Earth's surface. So it may change from area to area. Now, since maps are flat surfaces, they are really projections of the spheroid. They're in particular in hydrobid flood, we need to work with a projection. The hydrobid flood model works in a plane projection. So we need to use a projection. We cannot use the lat-long data that would be available from latitude to longitude representation of a surface. So we need to make a projection or use a projection. So the DEM and all the layers that we use in hydrobid flood needs to be projected in a plane projection. There are many different types of projections, mainly conical projections, where this sphere is projected on a cone, and that may be applicable to some areas. Then you have flat projections, that is just a plane, or cylindrical projections that also are used in some latitudes. Some of them are better represented for mid-latitude or for extreme latitudes, this one here, or for low latitudes at cylindrical projections. Now, the projections are something that is prepared normally by a software nowadays. So if you have one projection, you can convert to a different projection and make sure that all your layers are in the same projection system. So the projection just represents the Earth's surface in 2 dimensions, so it's flat. Of course, that flatness of the projection that is represented by this blue line over here, this is the one we're going to use, is not perfect. So there is a small difference, but provided that the area we are dealing with is not very big with respect to the Earth's surface, this is a very good approximation. Normally, in watershed applications and in riverine applications, we are dealing with areas that are at the most of lengths of hundreds of kilometers. And often case is only tens of kilometers. So if you have a city, maybe you have a city that is not more than a few tens of kilometers, wide, and when you apply a projection or you use a projection there, you are doing a very good approximation of the curved surface that it in reality is. So these errors may not pose an issue when doing modeling, and that's why we use that plane projection that is much simpler to handle than the spherical projection. One of the most common projections that are available is what is called the Universal Transverse Mercator, UTM. We'll often hear UTM coordinate system or UTM projection, and it stands for this term here. And one of the advantages of the UTM is that they cover the complete surface of the Earth. Of course, we will use the ones that are more appropriate for the area of our project, but the whole Earth is divided in 60 UTM zones. That these are vertical columns over here that cover from the North Pole to the South Pole. And they contain different sections that are divided. So each of the 60 zones are divided in different horizontal zones to get, let's say, a rectangle here that corresponds to the UTM projection. And these rectangles correspond to a flat surface that represents the projection of the Earth's surface. In particular, for Trinidad and Tobago, we normally work in that area in zone 20. If you go back to this slide, we can see here that this is the zone 20 here. And as you see here, this is the coverage of that zone. So we will be working with UTM, often with UTM zone 20 for Trinidad and Tobago. Now the coordinate reference system is also represented, besides the identifier of UTM zone 20, by this EPSG code. And it is important to remember this EPSG term because we are going to be using this code over here to represent this UTM zone 20. The QGIS system includes all of the projection, or can handle all of the projections that are available for the surface of the Earth, including UTM, all of the 60 UTM zones, and in particular the UTM zone 20 that corresponds to EPSG 32620. Now, don't worry about too many terms over here because we are going to be using them in the exercises that we're going to be doing. The point here to remember is that each of these zones have some metadata that you need to be aware of, and that includes the datum, that in this case, as you can see here, is WGS 84, is World Geodetic System 1984. And this is the ellipsoid that is used for UTM zone 20. And also, very importantly, that is in meters. Why is this important? Because as soon as you select your projection in QGIS, and in particular in hydrobid flood, you select this projection, and that also selects the unit system that you will be working on for the rest of the project. Normally, if you work in metric units, then you select this UTM zone in meters here. But in some areas that work with feet, they would select the same zone, but in feet. They are very similar. They are different in the EPSG code, but you have to be aware of that, because otherwise, once you develop your whole project, if you have the wrong length unit here, it will be very difficult. You will need to start from scratch in order to correct that error. Now, some other important points to keep in mind. The geographic coordinates do not correspond to any type of projection. So you, and also in hydrobid flood, we don't use geographic coordinates for the actual model data. The WGS 84 is the datum that we are going to be using, or the ellipsoid that we're going to be using to define the geographic coordinates and also the elevations. And remember that due to the fact that you may have different ellipsoids and different representations of the surface, sometimes the lat long data may correspond to the same lat long data may correspond to different locations. So if you're using an older ellipsoid, maybe data that is very old, and you see some lat long data there, that may not correspond to the same location as if you were using a different ellipsoid. So it's just something to keep in mind if you're using different ellipsoids or mixing that in your project. The last thing is that a datum has only one ellipsoid associated with, and it's so the thing is that you need to be aware that the datum is in a particular set of units and is associated with the ellipsoid that you will be using. So all of these things is not something that you will need to generate necessarily, but when you receive data, like a digital elevation model from some source, you need to review the information that that layer will have, and that will indicate the coordinate system, the projection, and the datum that you will be or is associated with that data set. So the second part that we're going to be looking at is the era of photogrammetric survey and LiDAR, that are surveys of the Earth's surface that can be used to generate digital elevation models. So on the direct method for elevation information surveys that we can use to create digital elevation model, we have three main types of technology: the radar image surveys, the aerial photogrammetric surveys, and LiDAR surveys. The radar image surveys, as the name implies, are obtained by radars that are located also in satellites, but it's the radar image that scan the Earth, and by scanning the Earth at different times and locations, they can obtain the surface of the Earth, or how it changes, and the mountains of depressions and so forth. This is a SAR is one of the standard radar images that you can use to obtain DEMs for the Earth's surface. Now, the service available on the DM website for radar, there is one that is widely used, and we have used it in several projects. It's a Global Digital Surface Model Project, a ALOS World 3D. It is a project of what is called the Earth Observation Research Center of the Japan Aerospace Exploration Agency. And it's based on an advanced terrestrial observation satellite that is called the ALOS 2. That's how it gets the name ALOS World 3D. And it uses synthetic aperture radar, so SAR, that is equipped with a panchromatic remote sensing instrument for a stereo mapping prism. So what it does is, this means is that as it scans the Earth, it scans not only in one position, but in different positions, obtaining a stereoscopic image of the surface. And by obtaining that stereoscopic differences, it can detect or infer the difference in elevations in the Earth. So this is widely used not only for obtaining terrain surface, but for different other purposes. Nowadays, it's also used even to obtain humidity of the water surface and many other parameters that are useful for other purposes. Normally, the resolution of this ALOS is 30 meters. That means that 30 meters is the smallest distance that it can resolve accurately. And also, coming back to our previous presentation, what you obtain from a SAR data is a digital surface model. That means that it has all the buildings or all the height of the vegetation. It's not only the terrain, but it obtains the complete surface, including all whatever you have on the surface and not necessarily on the terrain. This ALOS World 3D has many other characteristics that are indicated here about the resolution, and you have other quality information that you can also use to assess how good is the image for your particular area, because what happens is that due to since these satellites are moving all the time around the world, the resolution that they get is not the same at all the locations, and you have different parameters that you can use to assess how good that information is for your particular area. We had two experiences with this type of information. Once we used this for a project in Europe, and we were able to get a very good resolution out of the ALOS World 3D, that's sometimes called also AW3D. And we were very happy with the results and so forth. But then we tried to use it in South America for another project, and the results were very, very unsuccessful, if I can say the least. The quality of the DEM or DSM was not what we had expected, and that is due to the fact that the quality of this information varies sometimes very much around the Earth. So you need to be aware of that if you want to use this data. Now, how do you get this data? Well, you can obtain this information using the links that I point to here, and there are databases on these locations that you can download the data for different areas. There is also some products that are obtained from this data, and these are this is information that you can download for free, but there are some other websites or companies that use this information. They process or try to improve the quality, then they use it for other locations, and that is also called ALOS World 3D, but process in that case. You have also, for using the same or similar technology, the shuttle radar topographic mission. This was obtained by the NASA shuttle missions that were performed during many years, and also generate a digital elevation model for the globe, but not completely, because due to the orbits of these devices, they were not able to obtain beyond this latitude here, which is not a problem for us in this particular course, but anyway. So the resolution here is 1 arc second, so that's the resolution of the cells in general. This is the website that you can use to download information for this shuttle radar data. And if you want to use directly the data format that is provided in this, you can download a plugin. And this window that you see here, that we will be coming back to this window, is a window of the QGIS software that you should have installed in your computers. And if you manage the plugins, you will see that you can have a large number of free plugins that you can download. And one of them is the SRTM downloader that downloads data directly to your area of interest, and you can use that to obtain the data in the format that you require. Once you install the plugin, you will see that you have an icon that you use to activate the plugin. The advantage of this plugin is that it's user-friendly, so you can define the area that you want to download. You see that you have here the north and south parallel and west and east parallel, and then you very easily you can download the data, and you may need to register for that and then download the data, and what you get is essentially a raster that you can see here in grayscale. So this raster, as we discussed in last session, is defined by pixels, and each pixel has an elevation. So when you download this information from here, you already have that information stored in the pixels. Now the second set of data is probably the traditional one that you may be familiar with. It's a very old method that has been in use to generate photogrammetric stereo sets, and by flying and making photograph of the Earth's surface in different locations, you can obtain different photographs, and by analyzing these photographs, that knowing the angle at which they were taken, the lenses that they were used, and so forth, then you can obtain also the surface relief. So you get the elevations of the surface with respect to the plane that is taking the photographs. Now, knowing the plane elevation over the terrain, you can reconstruct the complete elevation of the area. Now, the advantage of this is that nowadays, instead of using planes, the new technology of drones have been adapted to use the same thing. And that's become much more popular, and also much less expensive than it used to be, because of the use of large planes that you needed, or planes that you needed to make this before. So has several advantages over, it's very fast, it's more economical, and it's very efficient, and that allows you to generate DEMs in a very fast way. Sorry. Now, some disadvantages is that the drones cannot be flown at very high elevation, so that restrict the areas that you could survey with them, and this typically restrict the areas to smaller watersheds or smaller urban areas, and also the flight time is limited because of the battery duration of these devices. And although this has become more and more, the batteries are better and better, and the drones are more efficient nowadays, and that is less of a problem now. But it's typically used for relatively small areas or small parts of a city that you want to analyze in detail to get a DM. And the third option, that is probably the most recommended one, is what is called the LiDAR. LiDAR stands for Light Detection and Ranging, and so that's LIDAR. and it's a way to use laser beams to determine the distance from a source to the surface. So you imagine you have a plane or a drone that is equipped with a laser emitter, and that laser emitter sends a laser beam to the surface and then register the time it takes to get back the impact location. And by knowing that, it will determine the distance to that location. So it's very accurate, very efficient, and it works normally also from planes or drones, and that allows you to fly the area of interest in a very fast way and also very accurate way. So the other advantage of the laser is that the LiDAR is that it can detect the difference in surface objects. So you can know if you have a vegetation or if you have a building, and then you can use this information to filter your final product so that you get, let's say, a digital elevation or terrain model versus a digital surface model. You see here an example of a set of a cloud of points that are LiDAR obtained, and you can see here that the quality of the points is different in the vegetation. You see here a palm tree, and you see here different forms, and this quality of the bounce back laser are used to later filter or process this information. Now, of course, all of these things need to be post-processed. Once you get the basic data, you need to get that data and process until you get your final product, that is a digital elevation model or a digital surface model. So if you have an initial point cloud obtained by a LiDAR, then you get a raw data that indicates very basic information about the laser beams or laser shots that were processed. And then you have to interpolate that information in order to get either a digital surface model or a digital elevation model. See here the difference that we were talking in the last session. You see here the digital surface model includes all the vegetation and buildings and everything that is on the terrain surface, while the digital elevation model, that is also called digital terrain model, is filtered, and you only leave the terrain surface, removing all the buildings and vegetation that you may have there. So the laser or LiDAR processing is very useful for this filtering of digital surface models and digital elevation models. Now, in terms of quality, just a comparison here, what you get from radar is not as accurate as what you get from a LiDAR. You can see here the difference. Nowadays, LiDARs can be sub 1 meter resolution. That means that you get resolution of objects are well below the 1 meter size, which is remarkable. While the radar is hardly below the 30 meter resolution. So if you don't need a lot of resolution, that's okay. But if you need a lot of detail for final designs or high quality simulations of hydrologic in urban areas, you need to look at this type of LiDAR data. Now, there is a big limitation of the LiDAR, that is that they normally are used to obtain the terrain surface, but when they go to a river, they just get the water surface. And that's the standard LiDAR. So you don't, when you have a standard LiDAR, and it goes to over a river, it will obtain only the water surface and not the bed or bottom elevation of the river. Now you have nowadays bathymetric LiDAR that is used to determine the depth of water by measuring the time delay between the transmission of a pulse and its return signal. So it actually penetrates the water. And this allows to have an approximation of the bathymetry or the topography of the riverbed underwater. So these are relatively new systems that are being employed more and more, but you have to be aware if that your source is a standard LiDAR, it will not determine the bed surface, but only the water surface elevation. That may be an issue that we will come back to. Now, in terms of file formats, the standard format for a LiDAR is the LAS, the LAS format. It's a binary file, and it's a public domain format, so it's a standard format that can be used to change information obtained by LiDAR methods. Then the last part of the presentation today is about techniques for making modifications to digital elevation models. We will have exercises where we will use different techniques, but in many cases we require to modify the raw data that we get for different reasons. There are situations where the information contains in the DEM has gaps, so you have cells or pixels in the rasters that do not have information, or that they capture vegetation that we want to remove, or they capture roads that or bridges, for instance, over the stream, and we need to remove that. So there are many situations where we need to modify the DEM. There are also situations when doing hydrologic modeling that the interpolation made is contain holes that are not representative of the actual terrain, and these are artifacts of the DEM and needs to be filled. That's the case of some situations where you get an artificial depression and then you want to fill it out in order to avoid getting water in areas that are not realistic. When you don't have data for some reason, maybe the LiDAR failed or the processing failed, and you get pixels where you don't have data, and you have a field no data tool in QGIS that you can use to interpolate elevations at these missing data points so that you will complete the information in an approximate way on the raster. Now, you can also make modifications to specific areas, and this is one example that is part of the exercises that we're going to be looking at. In this case, you have a river, and this is the river over here, but the digital elevation model includes the surface of the road that the bridge that goes over this stream. If you were to use this data in hydrobit flood, what will happen is that if you have flow coming from upstream here, then it will treat this as a dam because it's damming the stream. So you need to remove these elevations from the terrain in order to have a terrain that represents the flow surface and not the bridge surface. And for that reason, we will use different information. So this is the, let's say this is the original DEM. We'll construct a raster with the correct topography, and we'll integrate these two data sets to reconstruct a corrected digital elevation model that, as you can see here, includes the actual river through which the flow conveys downstream. So this is things that we are going to be learning in the exercises. So now we'll stop now. If you have any questions, we'll be happy to answer them.